Welcome to Oddly Real. I'm Nem Stefanovic. In this episode, we explore the nature of space and time and their role in what we experience in our reality. That sounds a bit heavy. Space, time, reality, those sound like big ideas, and they are. Regardless, we can start with an understanding of the foundations of space and time, and you'll see that there are natural implications for how it impacts our experiences. All right, so what does that mean? Well, let's say that you and I look at the same two events that happen, but we disagree with each other about when they occurred, where they occurred, or even the order of their occurrence. Sounds odd? Well, what if I were measuring the time of a ticking clock, but your time was flowing much slower than my time? What if I could leap across the galaxy in a single hop because its width was reduced to the distance no longer than the table in front of you? Now, we won't be physically doing any of that here, but that doesn't mean we won't be able to talk about it and understand why it's possible. If you stick around, you'll see it's all oddly real. So let's start from the beginning. Our human intuition tells us that there's a concept called space and a concept called time. We have always treated these as separate and distinct, and that makes sense in our experience. You can travel a certain distance in space. You can walk from the front door of your house to the tree in your front yard. And more importantly, you can measure that distance. You can take a unit of measure that you like feet, yards, meters, and you can figure out the exact distance you traveled using those units of measurement. Additionally, humanity has also been keeping track of time. Again, we have measured the passage of time by counting the number of days in a season, or watching sand fall through an hourglass, or using a stopwatch to time the number of seconds or milliseconds that has gone by since the beginning and end of a running race. All good so far? I hope so, since most of us wouldn't give these kinds of experiences a second thought. Measurements of distance and time are commonplace and typically treated separately. We can go one step further and define an event as something that happens in both space and time. Two people can arrange to meet for coffee at a cafe at 1 p.m. on a Sunday afternoon, and when that happens, that's an event in space and time. At some point later, the two people have finished their coffees and their conversations, and they've departed the cafe to head home. Another event. I want to emphasize that these events are real. They happened regardless if someone was there to take note of the exact meeting place or departure times using a map and a wristwatch. That's kind of a weird thing to say, that they're real, but you'll see why I'm emphasizing this shortly. Okay, so what's the big deal? All of this isn't new. Well, here's where things get a bit weird. It turns out that two people that measure the timing and distances between the occurrence of two events can in fact come up with completely different results. Not because of human error or issues with the measuring devices or different units of measurement, but because the laws of nature themselves. But that's not all. Things get even crazier since we can have situations where the two observers of two events even disagree on the order in which the events occurred. Confused? Awesome. Let me explain. We'll start with the famous example called the train paradox. Imagine a train traveling quickly. I mean very quickly, like approaching speeds close to the speed of light. There are two observers. One person, the train observer, is measuring distances and elapsed times between events while riding on the train. The other person, the ground observer, is measuring the distances and times between the same two events, but at rest on the ground, relative to the train as the train passes. In this example, lightning strikes the front and back ends of the rapidly moving train. Both the back end strike event and the front end strike event are observable by the flashes of light and the resultant damage at the location of the strikes. The ground observer is standing in the middle between both ends of the train. When the lightning strikes both ends of the train, the ground observer sees two flashes of light reach him at the same time. The ground observer notes that the lightning struck both ends of the train simultaneously. Now consider the observer on the train who is riding in the middle of the train. The ground observer sees the train observer riding towards the flash of light at the front of the train. The ground observer also sees the train observer riding away from the flash of light at the back of the train. It takes a little bit of time for either flash to travel to the train observer. The train observer is moving towards the front flash while moving away from the flash in the back, so the ground observer would expect to see the front flash reach the train observer first, followed by the back flash second. And in fact, this is exactly what the train observer sees. They don't see a simultaneous lightning strike at both ends of the train, but they instead see the lightning strike the front of the train, followed by the lightning strike the back of the train at different times. But this is not the end of the story, because you see, the train observer was standing right in the middle of the train. Additionally, they know from their basic physics that the speed of light is a constant. So if the light travels from the front of the train to the train observer, and if light travels from the back of the train to the train observer, all at the same speed of light, and leaving at the same time, they would have to reach the train observer at the same time. But they don't. The only possible explanation for the train observer, given their circumstances, is that the actual time that the lightning struck the front had to be different from the time that the lightning struck the back. That is not what the ground observer sees at all. The ground observer saw the lightning strike both ends at the same time. The actual timing of when the lightning strike events happened, as deduced by the train observer, were truly different from the strikes as seen from the ground observer. The two observers disagree with their observations of reality. So which observer is right and which observer is wrong? Well, actually, both observers are correct. As strange as this sounds, there's really no single answer to indicate that one bolt of lightning struck the front versus the back of the train. It's entirely relative to who is observing the results. If you're on the ground, in the train, or perhaps even in another frame of reference entirely, for example, a rocket ship traveling in the opposite direction of the train, all of these observers would see the lightning strike events differently. There's a name for this particular phenomena, and it's called the relativity of simultaneity. Okay, that's a lot to take in. Long story short, different observers can experience the same events quite differently. We saw that in fact the sequence of those events, like whether one event occurred before the other or at the same time, can lead to disagreement among the observers. So is that all that can happen? We disagree on the timing of events? Well, not quite. There's more. Let's take a look at one more example together. We're back on a train as the train observer, only this time there are no lightning strikes. Instead, we're using the speed of light to measure the passage of time. We have a laser beam pointed at the ceiling of the train where there is a mirror to reflect the light back down. When the reflected beam of light hits the floor, there is a mirror there as well that reflects the light back up. This reflecting beam moves up and then down and back up cycle after cycle. We count these cycles to give us a measurement of time while on the train. On the ground, we also have our ground observer who can see this all happening through the window of the train. However, the ground observer doesn't see a beam of light traveling straight up and straight down. Since the train is moving, the light actually bounces at an angle in the direction of the motion of the train. So the ground observer sees light moving in a zigzag pattern. So far, this is exactly what our intuition would expect. Well, here's the part where things aren't so intuitive. When light travels straight up at the constant speed of light and straight down at the same constant speed of light, you get a certain time measurement for that short distance. And that's what the train observer measures. However, the ground observer sees the same beam of light travel a longer distance at an angle in a zigzag pattern, but at that same speed of light. Since, from the ground observation, it takes the light longer to traverse each cycle, the ground observer's time measurement of each cycle is longer. In other words, more time has gone by for the ground observer per cycle as compared to the time for the train observer. You heard me correctly here. The flow of time is different on the train. It's slower as compared to the flow of time on the ground. There's a time dilation. And I know what you're thinking. It's probably this particular experiment. If we changed the timing mechanism, like used a watch or an elaborate atomic clock or something, instead of the beam of light, we'd get a different result. Well, no, you wouldn't. It's literally the passage of time itself which is now different between the two observers. The beam of light bouncing back up and down is just a very useful way to analyze the problem, but it has nothing to do with the reason for the time dilation. Going back to our example, the faster the train goes, the more elongated are the zigzags of the light-based clock as seen from the ground, and hence the bigger discrepancy between the time on the ground and the time on the train. The passage of time can be slowed down as close to zero as you'd like without reaching zero, as long as you travel with sufficient speed. And that leads to one more important point, that even the measurements of distance, not just times, by different observers can be different. So imagine you're traveling so fast that your time has slowed tremendously that to you on the train, it seems like you can cross galactic distances within seconds. Doesn't that contradict that the fastest speed in the universe, the speed of light, needs hundreds of thousands of years to traverse the same galactic distances or more? Well, in fact, we can reconcile this seeming contradiction. In that fast-moving train reference frame, the observer would also see distances contracted. So their slowed passage of time also requires lengths in space and even whole widths of galaxies to be compressed. Now, for the fast-moving train observer, traversing an entire galaxy is only a short journey. Okay, so depending on your reference frame, if you're at rest, moving or moving really, really fast, you experience the universe very differently. So what does this all mean? Is there no basis for reality at all? Do we all get different measurements for the same events, and are we doomed to disagree about reality? Well, interestingly enough, no, there is in fact a reality that we can all agree on despite our different experiences and observations. So first of all, despite all the differences in the measurements of space and time between observers, it's important to note that there is one crucial constant that does not change in each observer's frame of reference. That's the laws of physics. The same laws that explain nature's forces, the mechanisms of motions, and the mathematics that describe them is always the same. Even if the numbers in those calculations are different, the rules of nature stay the same. Second of all, recall I mentioned that events, a thing that happens in space and time, are real. Regardless of what time you think they happen, their order of sequence, or the distances in space, events happen, they are absolutely real. It also turns out that the separation between events, something called their space-time interval, is also quite real and absolute in its measurement regardless of what each observer sees. So what is a space-time interval? Since it became known that space and time individually were not absolute, and the observations of both were highly dependent on an observer's frame of reference, it was quite natural to start treating space and time together as a single unified entity known as spacetime. It also became natural to define the notion of a distance between events in spacetime that would be preserved and consistent between observers. Many of us are familiar with the regular concepts of distance in a 3D space. Slightly different, spacetime is a 4D construct with 3 dimensions of space and 1 dimension of time in one unified framework. The concept of distance in spacetime, or the spacetime interval, is computed by including the 3 dimensions of space as well as 1 dimension of time all together. Stated simply, the square of the spacetime interval between events is equal to the square of the time separation minus the square of the space separation of those events. When you substitute the values of these observed measurements from any observer's reference frame for the same 2 events, you get the exact same space-time interval. Voila, the true reality. So there's something more real about the space-time intervals than what we can observe ourselves looking at space and time separately. Now we finally have a basis for reality. One is an event, which is a combination of something happening at a certain time in space, and the other is a space-time interval, which is the distance separating two events in space-time. And our observations, which differ between us depending on our frames of reference, can ultimately be reconciled in this new space-time framework. But there's still one more thing that doesn't add up yet. We mentioned time as a dimension of space-time and mentioned that space-time is four-dimensional, 3 dimensions of space and 1 dimension of time. But isn't time something totally different than space? How can we compare something in time, which we measure in seconds or days, to something we measure in space, which uses kilometers or miles? And how can we just put the two together? Well, it turns out they're more similar than they appear. Much like we can measure a distance in space using kilometers, that same distance would appear to be different if we measured it using miles. We'd have different values for our results, and it wouldn't be clear that we measured the same thing. It turns out you can measure time not just in seconds or hours or days, but in meters or any other unit of distance. We are already somewhat familiar with this concept when we talk about light years or distance that light travels in 1 year of time. What we've done in this case is converted the time measurement into a distance by a constant conversion factor, the speed of light. Oddly enough, one way to think about this is that we've always been measuring the passage of time inconsistently for historical reasons, and for human reasons to make it easier to work with time in our everyday lives. It is surprising to see that the speed of light is really just a constant to convert classical measurements of time into a more natural form for its presence as a dimension in space-time. Does that mean time and space are actually the same? Well, no, they're clearly different. Time moves forward in one direction and it's always flowing in that direction. However, we can treat space and time on the same footing, where we can then make equivalent comparisons between the two as contributing dimensions in space-time. I hope you found this episode of Oddly Real interesting. I'll see you next time as we continue to explore unusual phenomena in our everyday world. And remember, really odd, really interesting.